Okay, today in this discussion, we are going to talk about the standard IEEE 1100, which is commonly referred to the Emerald Book. And this is basically recommended practice, so it's not a mandated standard, it's a recommended practice that basically outlines the principle and the techniques that are necessary for powering and grounding of sensitive electronic equipment. We are going to call them SEE. And in today's discussion, we are going to cover the system framework, how to design, what are the requirements for design and implementation. And as we said, we are going to use IEEE 1100 as the framework to make sure we have reliability, signal integrity, and electromagnetic compatibility in our system when we're dealing with the sensitive electronic equipment. Now, that IEEE 1100, as we mentioned, is a recommended practice, is not a mandatory standard. It provides the guidelines for powering and grounding the sensitive electronic equipment. This standard basically aims to prevent failure or data corruption or operational disruption in environment where even a minor disturbance, electrical disturbance, can cause significant damage or even downtime. So the traditional grounding method that we had before IEEE 1100, they are mostly focused on the safety of the electrical system. So they mostly designed to prevent electric shocks or fire. Now, when we have sensitive electronic equipment like computers or medical equipment or telecom systems, they also need some functional grounding approach. So we need to prioritize signal integrity or low noise reference planes and transient suppression. Now, the key objectives of this IEEE 1100 is to keep sensitive electronic system basically running continuously without any unexpected shutdowns or data loss or malfunctioning. Now, how we do that is basically we are going to talk about designing the power distribution and grounding system so we could avoid the unintentional or unexpected tripping or breaks. We are going to design the system to prevent logic fault, like for microprocessor, and minimizing the memory corruption when we're dealing with a digital system, and protecting the equipment from like physical damage because of like power disturbance like surge or harmonics. Now, as we said, the traditional grounding was mostly focused on a safety, okay? So it was to clear the faults and protect the people, okay? Now, IEEE 1100 introduced the functional grounding in addition to that safety grounding, which basically creates a stable, low impedance reference plane for our signal circuits. Now, we mentioned some of the aspects of what are the key functions of the framework or the recommendation in IEEE 1100. Let's go into those. We said we want signal integrity. So how we do that? We basically reduce the common mode voltage difference between the systems so we could prevent logic errors. Okay, or we provide noise immunity by suppressing high frequency transient that basically can cause coup into data lines. Now, we also need to have a stable voltage reference to make sure the functionality, the proper functionality of sensitive electronic system which we do that by bounding and grounding uh, the system and design those grounding system in a way to maintain the consistent reference plane. And it should happen across all the interconnected device in our system. Now, we said this standard adds functional grounding to the safety grounding. So we need to also think about and design our grounding system and power distribution system for safety too. Now, we have some disturbance when it comes to the power supplies. One would be the surge. Okay, so it's like transient from lightning or switching surge or inductive load switchings, and they can damage sensitive electronic, okay, or even cause error in their function. Now, IEEE 1100 actually recommend to use a surge protective device in our system, so we could properly coordinate those surge protection with the grounding system. Also, it recommends a proper bounding so we could give the transient a low impedance, a kind of like pass to the ground. So we basically guide the transient toward the ground system instead of letting them go through the sensitive electronic devices that we have. Another recommendation in this standard is coordination with a family of standards named IEEE C62, which is for surge protection kind of like devices. They are the details criteria for surge protection devices. Now, we also want to have a certain certain amount of like a certain level of the power quality conditions. So we make sure that we provide a clean, stable, and regulated power for our sensitive equipment. Now, there are some issues that actually is typical, is common, and it happens a lot in power system, like voltage sags, or voltage swells actually, or harmonics, or flicker and high-speed transient. Now, when we talk about the voltage sags and swell, basically those can cause computer reset. Okay, we know that the harmonics also, when we mention the issue of harmonic, they could be generated by nonlinear loads. Okay, and the effect of them into the system for our electronic devices is like creating an overheat in a transformer, or even like distort the waveform. So it could lead to some error in our data when we talking about the kind of like a very sensitive high frequency data transfer system that are very kind of like vulnerable to high level of noise. So what are the solution? Okay, the solution that IEEE 1100 recommend is to have isolation transformers or redundant feeders or UPS system and harmonic filters. So we could basically mitigate those issues and provide a high quality power for our sensitive electronic system. Now, IEEE 1100 is performance oriented. Okay, so it's designed for like mission critical environment. For example, data center or health facilities or broadcast and telecom or industrial automation. Now, we are going to talk about them a little bit further. Now, but who, as an engineer, who is going to use this IEEE 1100? Let's talk about that. The first group of engineers that using this standard are consulting engineers. Okay, so why they use it? Basically, those consulting engineers are the one who designing the electrical infrastructure, especially when we talk about the mission critical facility. That's kind of like become more important. It could be like data centers, as we mentioned, hospitals or telecom hubs, industrial automation plants. There are several kind of like sensitive fields that when consulting engineers are trying to design those infrastructure, they need to use this standard. Now, this IEEE 1100 basically provides them with some engineering best practices uh, beyond the safety, so they could make sure they have power quality, noise suppression, and system uptime. So uh, if there is a design failure, okay, as the result of ignoring IEEE 1100, when we're talking about the consulting engineers, that can lead to data loss or production downtime, or even like when we talk about the medical system and healthcare kind of like environment, even could have like a life-threatening failures. So that standard 11 IEEE 1100 is very important. Basically, is essentially it is essential for their design, basically providing a verification checklist when we're dealing with a sensitive electronic equipment. Now, another group of engineers, or like basically people that use this standard, are facility managers. Okay, so those facility managers are responsible for like ongoing operation. Okay, so uh, this standard helps them to detect and mitigate the issues basically proactively. Okay, so they don't need to like wait for a problem. They have to like be prepared beforehand. And that could be like monitoring grounding impedance and common mode voltage. We are going to talk about there are some criteria like threshold for a proper grounding impedance and acceptable common mode voltage that those facility manager should frequently check and make sure that they're maintaining those requirements. They continuously meeting those requirements. Now, there should be some also periodic inspection when we talk about the signal reference grid. We are going to go deeper into that concept, or bounding network interface. We're also going to talk about that in upcoming slides. These periodic inspection basically cause to ensure that those systems remain within the operational specification that they are designed for. Now, when we talk about the facility management, there is another aspect, the load management. Okay, so that means that we have to make sure that sensitive loads remain isolated from the noisy equipment. Okay, so IEEE 1100 defines some zone segregations that helps to isolate sensitive electronics equipment from those that could cause problem for the mission critical kind of like equipment. Now, the third group of people that use the IEEE 1100 are electrical contractors. Okay, so when we talk about meeting the requirement of IEEE 1100, one thing is to design the system based on those criteria, but we have to pay attention to the fact that implementation of that design has a significant effect on the outcome of the whole project. So it's not just the proper designing aspect. We have to make sure that the contractors that are implementing the designed power and grounding system, they also follow the requirement of IEEE 1100 to make sure they don't mess up with the design that was given to them. So, like, they have to make sure that they have proper grounding and bounding, or the conduits and cable layouts are based on the requirements. So, like for example, they use twisted pair or shielded conductor for the long runs. uh, or run hot, neutral, and ground conductor together in the same conduit, so they could reduce the like inductive noise coupling. So these are the kind of like the situation when we talk about the implementing those design. These electrical contractors, they have to make sure they're following the IEEE 1100 recommendation. Okay, if they don't do that, basically uh, they affect the design. They can nullify like the entire functional grounding strategy and lead to logic faults or equipment damage. Now, we said when we talk about the sensitive equipment, although they are actually exist basically everywhere, they could be in any kind of like environment, those sensitive equipment, but there are some environment that are uniquely vulnerable to those issues that IEEE 1100 covers. One would be the data processing center. So in those kind of like facility, we need continuous uptime, and it's very critical for the business operation uh, or cloud services and data integrity. So even a millisecond power disturbance can basically corrupt the database or even crash the servers. So the data centers basically operate with a high density of sensitive electronic equipment. There is servers, there is storage arrays, there are networking gears. They are highly susceptible to the voltage sags or transient or ground noise. So basically, we need to follow some practices that are recommended in IEEE 1100 to make sure we are addressing those problems. Like for example, there is a practice recommended by IEEE 1100 to have hybrid grounding and signal reference grid. We are going to talk about those concepts again in upcoming slides, or we could provide a redundant power topology. So we make sure we have an ongoing power supply. Uh, there is a harmonic control and load segregation. We already talked about those. So by using some K-rated transformers and harmonic filters, basically we make sure that the servers with a high nonlinear loads are kind of like don't face any challenges or issues that could jeopardize their functionality. Now, another very kind of like vulnerable environment is healthcare facilities. Now, we know that the medical equipment like MRI or CT scan or surgical robots, uh, when we talk about those equipment, even a momentary power kind of like disturbance can cause some like errors in diagnostic or even like a surgical interruption. You can imagine this is how severe the consequence of those issues could be. So we need to make sure we follow IEEE 1100 to address those vulnerability. There are several practices recommended by IEEE 1100 for like healthcare system. One is like a functional grounding for medical electronics or a strict voltage and transient control. Okay, so there are very strict criteria when we dealing with the medical equipment. And there is a clean power supply recommended also, like a double conversion UPS system. So we make sure we have a clean voltage, clean power supply. When we say double conversion, we mean like we have like an AC, then we convert it to the DC, store it in a UPS, and then when we want to like supply the medical device, we convert it to the AC again. So we basically isolate the plug-in AC with the AC the distribution power grid. We isolate that grid from the equipment that are supplied by that power. Now, another environment is broadcast stations, like TV and radio stations, stations that signal quality and the continuous transmission are very kind of like a critical aspect of their operation. So they have to have like some proper grounding strategy or EMC, electromagnetic compatibility and surge protection. So, or light load isolation. So we make sure that we don't lose transmission or we don't face poor signal quality and like some expensive equipment damages, which basically means revenue loss. Another environment is industrial automation, like SCADA system, PLC networks, and like a robotic installation control. Basically, those systems control the entire production lines or any distribution system, and any kind of like variation or disturbance basically leads to a production downtime or safety hazard. So we need to, like, for example, have load segregation and zone design. We are going to talk about that. Grounding and signal integrity is very important. And when we talk about the safety, the surge and harmonic control also become a very critical aspect of these recommendation by IEEE 1100. Now, this IEEE 1100 is not exist in isolation. There are some complementary standard that we need to know about them. Now, why this integration with other standards is critical? So the recommended practices, okay, in IEEE 1100 is specifically for sensitive electronic equipment, okay? But we have several other standards that provide minimum safety requirement, for example, or general power system guidelines, where the IEEE 1100 basically refines and extends them for performance and reliability. Now, we need to make sure we follow the regulatory compliances or power quality and noise mitigation or grounding integrity and system reliability in addition to the requirement given by IEEE 1100. Some of these standards are like, for example, IEEE 519, which is for harmonic control of the power system, defines some limit for current harmonics and voltage harmonics. So we make sure that we deal properly with the problem of the harmonics. Like, for example, in IEEE 1100, we require a harmonic distortion, the total harmonic distortion, THD, less than a 5%. But how we could like deal with it, or how we could like define that criteria, we need 519, IEEE 519 for the process of defining the THD, measuring the THD, and all those problems. Now, I want to like make sure that you note the fact that IEEE 519 has several requirements. One is the individual harmonic limitation, current harmonic limitation, and voltage harmonic limitation. We have two distortion parameter that quantifies the level of distortion. One is THD, another one is TDD. THD is total harmonic distortion. TDD is total demand distortion. Now, when we talk about the overlap of IEEE 1100 and 519, IEEE 1100 requires a THD less than 5%. That's very important. Now, we might have some K-rated transformers for dealing with a harmonic. Also, we need to make sure those transformers are in compliance with IEEE 519. So there is quite of a detail that the practices recommended in IEEE 1100 needs those IEEE 519 definition to make sure we are designing and implementing a proper system. Now, another standard that is complementing or like completing the IEEE 1100 is IEEE 142. Another name for that standard is Green Book. That standard provides fundamental grounding topologies for industrial and commercial systems. So when we're dealing with that, we need to also consider the IEEE 142. Next one is the family standard of IEEE C62. Okay, this is a family standard and it covers the basically guidelines for surge protective devices. We need IEEE 1100 basically recommend using the surge protective devices in the design of our grounding and power system. But what are the criteria, specific criteria of those systems that where that C62 family kicks in and defines those details? We also have the NFPA 70, which is a national electrical code, and basically set the minimum electrical safety standards for wiring and grounding. Okay, so this is the aspect of the grounding system. When we said that like there is one aspect is safety, another aspect is functionality. And when we talk about the safety, beside IEEE 1100, we need to also follow the NFPA 70. That way, we could make sure that we're completing the whole mission and now we have a proper design and implementation. Now, let's move on to more topics related to the 11100, IEEE 11100. There are some key definitions that before we go deeper into that standard, we need to like make sure we know those definition and we are in the same page with each other. Now, one is sensitive electronic equipment or SEE. This SEE refers to any electronic device or system, okay, that failure, misoperation, or data corruption due to the electrical disturbance can cause data loss or production downtime or safety risk or financial losses. So this is the definition of the sensitive electronic equipment. Now, the key characteristics of these SEEs are like they have high susceptibility to power quality issues, like voltage sag or transient or harmonic or EMI, electromagnetic interference. Example would be like data server or PLCs or SCADA system. Now, another definition that we need to like make sure we are familiar with is the signal reference grid, SRG. The SRG is a mesh of interconnected conductor. Usually we use copper strips, forming like an equipotential reference plane. Equipotential means through the whole mesh, through the whole network of interconnected conductors, we have same voltage when we talk about the voltage of that mesh compared to the terminal of our ground in our building, in our facility. We know the voltage is between the 2 points. So when we talk about the equipotential reference plane, we mean the voltage between that plane, that grid, and the terminal of the main terminal of our grounding system in our facility. Now, another definition is common mode voltage. We mentioned that briefly before, but what is the CMV or common mode voltage? CMV is the voltage difference between the neutral and the ground. And it is measured at the terminal of the electronic device. Okay, that's very important. voltage difference between the neutral and ground, okay? And it's measured at the terminals of the equipment, okay? The input terminal of equipment. Now, you already know that theoretically we want the ground voltage to be zero. It's not going to be exactly in real world, but we need to be zero. Now, if there is a voltage difference, and in a single phase AC system, we normally, like in the source part, we normally ground the neutral. So if there is any voltage difference between the neutral and ground, that means somewhere down the road, or like in either in upstream or downstream of our network, we having a floating voltage. So somewhere the grounding is messed up. Okay, so now our neutral gaining voltage. Uh, there is a limitation. We are going to talk about that common mode voltage should be less than a 1 volt RMS. Another definition is bounding network interface, BNI. Okay, that BNI is the designated connection point, okay, where the signal reference system, that SRG that we talk about, interfaces with the boundings grounding electrode system. Sorry, uh, the BNI is the point when the SRG connects with the building ground electrode system. So that points that SRG is connected to our facility ground. Now, when we saw these and we talked about these definition, let's go to the fundamental principles that we have to keep in mind when we talk about the powering and grounding system. Now, the IEEE 1100 basically sees the powering and grounding system in 4 subsystems. Okay, the first one is the power distribution system. Now, this subsystem is responsible for delivering the electrical energy to our equipment. And it should do that within an acceptable voltage, current, and frequency tolerance. Okay, so there are criteria, there's a limit for voltage stability or waveform integrity or transient kind of like mitigation, load segregation. There are requirements in IEEE 1100, so make sure that the power distribution delivers a proper power quality energy to our system. Next subsystem is grounding system. Okay, that grounding system provides the reference point, and this is for both safety and operational voltage. So, like in IEEE 1100, that grounding is actually is actually viewed not just as like a safety feature, it's also a functional infrastructure. Okay, so we have criteria for ground impedance for different scenarios. Okay, so we are going to talk about those criteria, or we have some recommendation for topology selection, how we have to design the topology of grounding system. So we make sure we following the threshold and requirement of IEEE 1100. Or that BNI that we talked about. What is the recommendation for bounding network interface, where this SRG or reference ground will connect to the building's grounding electrode. Now, next subsystem is signal reference subsystems. This system basically establishes a uniform equipotential reference plane, that SRG that we'll talk about, okay, for all the electronic equipment that are interconnected So we make sure we have a signal integrity and noise immunity. Uh, there is another aspect, another subsystem in the powering and grounding systems, which is the electromagnetic compatibility subsystem. Okay, this part controls basically the propagation of both radiated and conducted electromagnetic interferences. Okay, that way we could make sure that we are maintaining the equipment compatibility and the regulatory compliances. It could be like providing some shielding kind of like infrastructure to avoid the radiated uh, interferences, or having a proper grounding so we avoid conducting interferences, or isolation when we isolate those equipment that actually creates those interferences from those equipment that are sensitive to those interferences. Now, when we talk about a power system, a powering and grounding system, we said there are some requirements, some threshold that are mentioned in IEEE 1100. Okay, let's go over those. These basically criteria make sure that we have a high reliability power and grounding system. Now, the first one is the grounding impedance. It's important because if we have a high grounding impedance, that means the SRG, or the point of connection at the terminal of the equipment, at the input terminal of equipment, the point of connection to the ground would gain voltage, because we will gonna have noises, we will gonna have some surge current, we will gonna have some neutral current, or like a failure that cause rush current in our system. And the design of each equipment is to guide those unwanted currents through the grounding system to the building's ground. Okay, now if we have a high impedance in our grounding, that means the point of connection in the terminal of the equipment would gain some voltage. Now, the criteria, the recommended limit for grounding impedance is less than 1 ohm from the input terminal of the equipment to the SRG. So whatever wiring that you use in your system to connect the plug-in of your equipment, the power supply of your equipment, to the SRG that we are going to talk about, that is we developing for creating the reference equipotential reference plane, the connection should be less than 1 ohm. Okay. Now, we already mentioned we have some parameters named common mode voltage, which is the voltage between the neutral and ground at the input terminal of our equipment. Now, the recommended limit for that parameter is that the voltage between neutral and ground should be less than 1 volt RMS. This is measured at the input terminal of the equipment. Now, we are dealing with the AC system, and we know that the AC system would alternate by having like a half positive cycle and half negative cycle. So there is a concept of the zero crossing when we talk about the AC system, but theoretically, we have a smooth zero crossing, is a sinusoidal voltage, but that's not going to happen in real world. When we have a zero crossing, there is always some distortion. It could be because of the switching devices, or even like the regular devices, when they uh, cross the zero, okay, they've also experienced some distortion. It could be because of the hysteresis effect in our inductors, for example, that do not let the voltage or current easily reverse the direction. So we would have some distortion when the waveforms, either voltage or current, crosses the value zero. So goes from positive half cycle to the negative half cycle or vice versa. The limit recommended for sensitive equipment by IEEE 1100 is that distortion should be less than 1%. We are going to use the THD, okay, formula to measure that distortion. But the window is not full cycle, is limited to the interval when the waveform is crossing the zero value. We said some of the disturbances in power supply is, for example, voltage sag or so. Okay, so it could be drop of voltage amplitude or increase in voltage amplitude. Now, the voltage sag, for example, has two parameters that defines the intensity of the voltage sag. One is the depth of the voltage sag, meaning the amount of dropped voltage. So like we have a nominal voltage that the voltage should be. And when we have a signal, the sag, the voltage sag, that means the voltage dropped to another level, an undesired level. The difference between the desired level and the real level, the undesired level of the voltage sag is the depth of the voltage sag. Now that drop of voltage, that sag in the waveform would not be like instantaneous, like in one fraction of like a nanosecond or millisecond. There is a duration for that voltage sag continues to exist. That duration is voltage sag duration. Now we have limits recommended by IEEE 1100. The voltage sag depth should not be more than 10% of nominal voltage. So maximum voltage sag deviation should be 10% of our voltage, our nominal voltage. And also we should not have voltage sag more than 10 milliseconds. So the duration of the voltage sag is bounded by the limit of 10 milliseconds. Now, we said that our sensitive equipment are also vulnerable to harmonics in the power system. So we have to limit those. We already mentioned briefly the recommended limit for THD is 5%, and we have to define the THD based on IEEE 519. Now, these are basically the limitations that are recommended by IEEE 11100 for different type of problem that we could face when we talk about the power quality or the quality of the power system and grounding system in our network and facility. Now, we said that the traditional grounding system is safety oriented kind of like system. So it focuses on fault clearing and personal safety. They are designed to carry fault current, and they are designed to do that temporarily. So it's happened during the fault. Okay. The impedance value is designed based on the fault current magnitude, not signal stability. And when we talk about the safety ground, when we design them, they do not consider the high frequency transient when they design the grounding system. So they always set the impedances and the design for low frequency fault current. That creates some limitation. IEEE 1100 at functional perspective, functional performance perspective, which basically reframes the ground. Is not just for safety anymore. It's for operational signal reference plane also. Now, based on this IEEE 1100 standard, now our ground path should be electrically quiet. What that means? Electrically quiet means minimal transient noise. Okay? Or it should have low impedance for both power frequency and high frequency ranges. Okay? And also it should be free from any circulating current. Okay? Those circulating current can result in a voltage offset or increase in that common mode voltage. Okay? The CMV that we had. So we already covered some of the design principles like low impedance grounding. When for power frequency, we have to limit our impedance on less than 1 ohm. And when we talk about the high frequency aspect of the ground impedance, the limit become 1 milliohm. So power frequency 1 ohm, high frequency 1 milliohm. Now, he said that one of the tools that we could use to have a proper grounding system is to design a proper topology for point of connection to the building's ground. How we connect the our S or G to the building's ground. Now, we have 3 different topology. One would be the single point grounding, another one is multi-point grounding, and the third one is hybrid, which is the combine of SPG, the single point and multi-point. Now, we do that to provide, we design those topology to provide a stable low noise reference plane. So we could make sure that our sensitive equipment work properly. And there is the safety kind of like aspect and the EMC requirement in those design. Now, in the single point grounding, all the grounds terminate at a single point. So it's like a star connection. So there is only one bonding point between the equipment chases and the building ground system. Okay. Normally, we use that as in a low frequency, high sensitivity analog system, like audio and recording studio, or medical imaging, or like low frequency or F system. And this SPG has some pros and cons. Okay, so that single point grounding. One of the pros is that in a low frequency system, it controls the circulating current. So it eliminates the ground loop because there is no loop actually. All the systems are directly connected to a BNR, to the building's ground. It also provides a single defined reference potential. Okay, so minimizing the analog measurement error. But there is a limitation. When we dealing with a high impedance, when we dealing with a high frequency, we are going to see high impedance in those single point grounding system. Okay, because we have long ground leads which will act like an inductor, and we know the impedance of inductor is J omega L. So higher distances, higher grounding paths, meaning higher L, meaning higher impedance when we talk about the frequency, and is J omega L. So when we increase the omega, the frequency, then that impedance also will increase. So single point connection has a vulnerability when we talk about the high frequency range. Now, we said the next topology is multi-point ground. The multi-point ground connections are basically made at various points. So it's like a mesh kind of configuration. And it's normally kind of like implemented based on that signal reference grid, that SRG that we talk about. Okay. These kind of system is normally used in highest speed digital or broadband system like data centers or broadcast and telecom facilities, or like high frequency industrial automation system. Now, this system, the pros of this system is that they have a very low high frequency impedance because we have multiple short parallel ground paths which reduce the inductive impedance. So it provides a fast transient dissipation. Now, it also improves the EMC, the electromagnetic compatibility, by reducing the radiated emission and susceptibility to external EMI, which do that by providing that low impedance return path that we talked about. Now, what is the limitation? Is also have cost. Now, when we talk about the multi-point grounding, you can imagine that there is a vulnerability to circulating current. Now we have some loops that at low frequency can create a problem of circulating current, which introduce noise into our basically analog sensitive equipment. We said there's a third kind of like topology, which is a hybrid, so combination of the single point and multi-point. It wanted to like basically balance the advantage and disadvantage of the both. Okay, so in most of modern facilities like data centers or aerospace or hospitals, we normally use that hybrid grounding because system normally have some both of analog control circuit and high-speed digital electronic. So we need both aspect of the multi-point and single point, the advantage of the multi-point and single point grounding. Now, we said we have some aspect, we have some requirement when we design the power distribution system. Is not this IEEE 1100 is not just about grounding. It also have recommendation for power distribution system. We said we have to have voltage stability. Okay, so there is a margin defined in this standard for variation in the voltage, in the amplitude of the voltage, in RMS of the voltage actually. So we have to maintain our nominal voltage within the plus minus 5% of the voltage in a full load condition. That's important. Full load condition. Okay. Now, we should have waveform integrity, meaning we shouldn't have high distortion or Switching transient or sag propagation. We need to have a high quality reference ground that makes sure we have a low impedance bounding in our ground system and in the connection of the power distribution to the ground system. And we have a 0-volt reference, that common mode voltage between the neutral and the ground. It's where the power distribution and ground meet each other. Okay, so we should have a 0 kind of like volt reference. Okay, so we don't have to have we shouldn't have a, a common mode voltage exceeding. We already know the criteria. It shouldn't exceed 1 volt RMS. Now, we already talked about the load isolation. This is another aspect that comes in play when we talk about the power distribution. Okay, so the power supplies, the system of distributing the power and energy in our system should be isolated. Okay, so what I mean by isolated? So we have some sensitive equipment, we have some normal equipment, and we have some equipment that actually creates distortion and problem. We have to segregate those by defining the zones. So the power distribution system for each zone should be isolated from each other. We shouldn't have like a one panel board that supplies every equipment in our system. We have to categorize them. We are going to talk about the zones defined in the IEEE 1100, and each zone has to have a different isolated power distribution system. We could have several topology in our power system distribution. We could have a radial distribution, which means we have a single feeder. So there is one connection point to the power grid, to the external power grid. We have single feeder, which supplies multiple panels. Okay, that doesn't mean that single feeder is directly connected to all the equipment. We said we have to have load segregation. So that feeder supplies multiple panels. Okay, those multiple panels is each is for like a specific zone. Now, if we have a failure in upstream on that feeder, that means we lose the entire system. That's the the kind of like the limitation or problem with this topology. But it's significantly cost effective. Okay, so there is a very cheap kind of like implementation, and it's very simple to design because it has fewer components. Now, we could have another type of topology that we call it primary selective distribution. In this topology, we now have two independent feeders. Okay, they are connected to those panels as a redundant of each other. Okay, so if one gets out, another one kicks in and start powering the system. So that problem that we have, if we have a fault in a feeder, now we don't lose the supply. Or if there's a high disturbance in the feeder number one, we could manually or automatically transfer to the feeder number two and make sure we're meeting the criteria for power system. Now, it increases the reliability. Okay, normally is used for medium-sized critical system like hospitals or labs, like university labs, or like in manufacturing with a moderate downtime tolerance. But it's not as instantaneous power transfer. Okay, it doesn't have instantaneous power transfer between the feeders unless it's fully automated. Okay, this is one aspect of the disadvantage. Another one is that you can imagine it's more expensive than the radial distribution because we have extra feeders and extra component. Okay, and it's the design of these kind of like topology is more complex than radial distribution. Third topology is secondary selective topology, which we have a redundant UPS plus a generator. Now, in that topology, we have a fully redundant dual power source, okay, which normally often works in a parallel or hot standby situation. Now, it has a highest reliability. Okay, there are tiers defined for reliability. You can search on that, and there's a standard for that. These secondary selective normally provides tier 3 plus or even tier 4 reliability, okay, which is very good for data centers. These secondary selective are automated, so it has automatic instantaneous transfer when we have a failure in one of the sources, and is normally used in like a mission critical environment when we have a sensitive electronic equipment. Now, we said there is an advantage. We have a full redundancy that makes sure continuous uptime. We support load sharing in this configuration and hot maintenance. So if we have to do maintenance, we don't need to eliminate all the sources. We only kind of like de-energize the specific part that we wanted to like do the maintenance, while the rest of the system is still working in a nominal operational condition. But there is a disadvantage too. You can imagine it's a very kind of like expensive when we talk about the installation and maintenance of this system. And it requires a very careful design because we have to avoid circulating current between the sources. Now, we mentioned briefly that the transformer in our power system distribution plays a critical role when we talk about the power quality that are delivered to our sensitive equipment. It's not just about the voltage conversion, like a step up or a step down, kind of like voltage conversion. Okay, these transformers also serve as a filters and isolation barriers and even noise sink. Okay, so IEEE 1100 requires some selection criteria when you want to like select the transformers that you want to install in your system. One is the K rating of the transformer. You can see the K rating of the transformers, the table in the slides. This is the table of the K rating. The definition is that the K rating basically indicates the transformer's ability to handle the harmonic current without getting overheated. Okay, so the IEEE 1100 asks for minimum K13 rating. Okay, higher than that is also acceptable. This is a minimum, and we normally use, like when we talk about the very extreme harmonic conditions, you might want to like move from 13 to K20 or K30. Now, non-K rated transformer will overheat and fail when we talk about the harmonic reach conditions. Okay, now the transformer also have an impedance rating, and the recommended range for the transformer used in a sensitive electronic equipment is 2 to 4% impedance, and it's for power frequency impedance. Okay, so the lowest impedance the transformer should have is 2%. If we go lower than the 2%, it basically the transformer allows high inrush current, which means a lot of tripping and voltage dips for the other loads that are connected to that transformer. And if we go higher than 4%, it would cause some excessive voltage drop, when we have like a dynamic load changes. So we balance it up, those problems, by setting the impedance between the 2 and 4%. This way we make sure we control inrush current and we have a minimal voltage sag propagation. All the transformers should have a grounding resistance. When we talk about the IEEE 1100, the limit is less than 5 ohm. So this limit is for the service entrance ground electrode system. Okay, this 5 ohm, please don't get it confused with that 1 ohm criteria that we said. That 1 ohm criteria is for SRG, for the signal reference grid. This 5 ohm is for service entrance ground. Okay, because the transformer is in the entrance of our power distribution. Now, these are the recommended criteria from the IEEE 1100 for the transformer that we use in our power distribution system. Now, each power distribution system also has some panel board that basically distribute the power between the equipment. Now, they also have some requirement that is recommended by IEEE 1100. We do that recommend to make sure we have a clean, stable, and noise-free power delivery when we talk about the sensitive electronic equipment. Now, what are those recommended? One is we have to have isolated ground bars. What that means? So we have a dedicated ground bar connected directly to the signal reference grid, that SRG that we talk about, and is independent of other equipment grounding conductor. That way we stabilize the ground reference and provide that low impedance, less than 1 ohm connection. Okay. Another one is neutral to ground bonding. So we need to maintain the neutral to ground bond only at the source transformer. This way, we prevent parallel neutral ground passes. So we avoid circulating current or having a common mode noises. We have to avoid sharing the neutrals in the panel. So we have to provide separated neutral conductor for each of the branches in our panel. Okay, this is very important because nonlinear loads generates like triplet harmonics, like third harmonic, ninth harmonic, 15th harmonic. And if we have a shared neutral, they do not cancel in the neutral and basically add up arithmetically. We mentioned several times we have to have load segregation. So we have to have separated panel boards for different load types. There is 3 zones defined by IEEE 1100. One is zone A, which is the sensitive electronic equipment only. We have zone B, which is the mixed use loads with the isolation transformers or filtering. And we have zone C, which is a high interference load. The zone C equipment are the one that would create the problems in our system. Now, when those load segregation is very important. It's very important. We said like zone A is exclusively for SEEs, sensitive equipment. Zone B is mixed, but it should have filtering. And zone C is high interference, so the problem-making equipment. We need to isolate the sensitive equipment. This way we mitigate or reduce those problems. We don't have EMI. We control the EMI. We control the crosstalk. And we control the radio frequency interferences when we talk about the system. And don't let the zooms kind of like affect each other. Now, sorry. In a sensitive device, we also use UPS and bypass infrastructure because it's important for us to continuously supply our load. Okay, so we need to make sure that we have a good selection, a proper selection in our UPS. Okay, so the recommendation is to have online double conversion UPS for our sensitive equipment, and the voltage regulation should be within the plus minus 2% under the dynamic load, and the frequency difference, frequency variation should be less than 0.1 hertz. So plus minus 0.1 hertz. We have to have a fast transfer capability, okay, in case any of the sources are failing. We have to have full isolation paths for UPS services so we don't disrupt the critical load supply. And we have to have a transfer switch, like break before make switching, to avoid circulating current between the sources. We already talked about the grounding architecture. We said we have a single point grounding architecture. We have a multi-point grounding architecture and hybrid grounding architecture, and we use those. We select those based on the application of our grounding system. So in a very kind of like a small network, we can use single point grounding. If we have a highly sensitive, uh, medium sensitive, not highly sensitive, medium sensitive or large networks, we need to have multi-point grounding. And if we have like a very high sensitive system, when we don't want interruption or a low power quality at all, then hybrid grounding kicks in and help us to maintain that quality. We mentioned the signal reference grid, the SRG, several times, and we said this is basically the network or a mesh of interconnected conductor. You can see in the picture there are some like copper strips shaping a mesh, and it's underneath like our facility, and every equipment, the ground of every equipment should connect to that SRG. Okay, so this is important. We already said there is a requirement, so the space between these strips should be between 0.5 to 2 meters apart. Okay, these dimension of these squares. And when we talk about the radio frequencies, the impedance, the target impedance is less than 1 milliohm. Okay, and the designated point where the signal reference system connects to the building ground, okay, is very important. We have to make sure that we don't have any floating ground on that bounding point. Now, at the beginning, we said one of the problem in the power system, which was already addressed in the previous traditional grounding system too, is the surge problem. So we have to have surge protective devices. We have several type of surge protective devices. Like type 1 is the service entrance. So it's normally work with a high energy, high impulse current, and it's installed between the secondary of the service transformer, the entrance of our facility, and the line side of the service disconnect. Okay, now we have type 2, which is a distribution panel. It is inside our panel boards. It's a moderate energy clamping. Okay, and basically it predicts branch in the panels. Okay, and we have type 3, which is a point of use. These are connected either at the point of connection of each equipment or inside the equipment. So they could have like a control the low kind of like energy voltage speeds, voltage surges. This is our discussion for today. So basically, IEEE 1100 is not just guideline. It's actually a blueprint for electric reliability when we talk about the modern or mission critical facilities. It transferred the code compliances, okay, from the safety only to the safety and performance for grounding system. If you follow that, it's not just keeping the lights on. You are basically make sure that the data flows, processes run, and lives are protected. Thank you very much. If you have any question, please let me know. Otherwise, this is today's discussion.